font size too high. Oh. Okay. Hi, Chris. Hey, Omar. How's it going? Let's see who's turned in the homework. Squeeze me. All right. 30 students. Nice. Oh, my tea. Oh, jeez. Yum. Oh, wow. Was there some kind of miscommunication? Is there a reason why there's like no one in the chat today? All right. Well, even though that's a little sad, I think we gotta keep going. So, let's begin. Right. So, actually, you know what? I did say we were gonna start at 10, but hey, Sarah. Good morning. Yeah.
How can I help?
No, I said Sarah, not Siri. let's see. Yeah, I'm always on at 10, so I'm just wondering what's taking so long. Let's say, I guess we can start at 10:03. Grandmaster. Huh. Yeah, that's, hmm. Yeah, I feel like that's not a safe assumption to make. So, Hi, Tune. Good morning. Good morning, Dimon. Oh, Dimon, I forgot to call. I'll call you. Okay. Nothing serious. Okay. The short answer is yes. I just want to talk to you a little bit about it. Again, nothing serious. All right. Well, we had 10, and then went down to 9, and went down to 8. It's 10:03 now. Let's get started. Okay. So the very first problem. Good morning, Justin. Okay. I want, like I said yesterday, like today, I want to go over new material after we go over the homework. So, hey, Chris, for that reason, it's not on the doc cam because I want to transition to the board. Okay, so here we go. For number 1, we did that. Number 2, B, right? This number 1B is telling you to point your finger to the left, and it experiences a force out of the page. So your thumb points out of the page. So all that means is like this, which means that there is a uniform field pointing down for that object. All right, so it points down. Okay, I've drawn that there. All right, cool. For problem C, okay, I'm just gonna. Oh, okay. For problem C, I hope we can see. Yes. Okay. In which direction is this negative charge moving? Because it's a negative charge, I want to use my left hand. Its force points up. That's my thumb. Its field points to the left. Cool. Which means my pointer finger now is pointing into the page. So the negative object in number C points into the page. Okay. Let's go to number D. Letter D. In which direction does the magnetic force point? This is also a negative charge, so I'm going to use my left hand. Its velocity points this way. Its field points out of the page, so my middle finger does this. Okay? And my force, you can see, points this way. Okay? Right there. It points northwest. Letter E. Okay? Where is the magnetic field pointing? The charge is negative. The answer would be into the page because if I align everything correctly, my velocity is up, my force is to the right, then my middle finger is pointing into the page. So the field points into the page. Wonderful. And then lastly, for part F, where does the field point? Okay, if the charge is moving into the page, okay, and my force is down, then my middle finger now points to the right. Okay? Cool. All right. Good morning, Ethan. Good morning, Jared. You guys are a little late. You know, I stayed up really late too. I'm not in the best mood. I stayed up until 5 o'clock. I have no idea why. I just couldn't sleep. Yeah, so I'm really tired right now, but we still out here, right? Obtaining this grain. Okay? So number 2, I thought was a really cool problem. If you guys ever wondered how we determine the mass of the electron and the mass of the proton, like, because if you really think about it, if the electron has a mass of 9.11 times 10 to the negative 31 kilograms, and excuse me. And the proton is of an order of 10 to the negative 27, there is no scale or triple beam balance or anything that exists that can measure that small of a mass, right? So we need a different way of doing it, right? One really cool way to measure mass that we saw in the previous semester was a good morning, Ainaba, a simple harmonic oscillator, right? If I know the stiffness of a spring, and all I know is the stiffness of the spring, and I attach a mass to it, and I let it shake, and I measure the period, I can measure the mass of the thing hanging just from the period and the spring constant k, right? Because the spring constant was just, the period was t equals 2 pi, the square root of m over k. So if I know t and k, I can solve for m that way. Remember, that was like a really cool way to measure the mass of a particle without anything, without looking at force, without looking at like torque and stuff of a triple beam balance. But again, how the heck am I going to hang a proton or an electron off of a spring, right? I can't do that either, right? And the best way we have to do, the best way with which we have to do that is this kind of device, all right? So I shoot charged particles at constant speeds, okay? And because the velocity is perfectly perpendicular to the magnetic field, it will experience a force that is both perpendicular, to both the velocity and the field, which confines the force to this plane. So it's always going to be on this plane. It will never have a component pointing in or out of the page. And not only that, the force will always be perpendicular to the velocity, which sets up our conditions for uniform circular motion, right? Anytime I have a constant force that's always perpendicular to my velocity, I'm never going to change my speed, right? Because to change my speed, I need a component of my acceleration or my force that's parallel or anti-parallel to my velocity. And because it's perfectly perpendicular, the only thing I'm doing is changing direction. And the only thing I'm ever doing is changing direction. And I'm not changing speed, which means these particles are attending the University of Central Montana, which, like most other colleges and universities, and like us, are implementing remote learning, okay? So, which is unfortunate for the students there and all the particles that attend, right? But fortunately for all the particles, remotely they can still orbit circular trajectories with a constant speed, right? Yeah, so what do we have here? We have a charged particle. I'm going to call it Q. It's initially traveling with the speed v, but we know eventually it's going to take a circular path, right? Right? There's my force. There's my force. There's my force. There's my force, right? That force is the net force in the horizontal direction. If I'm looking at this from a bird's eye view, right? I don't really care about the up-down direction, which would be out of the page into the page, right? So I'm saying my net force is simply the magnetic force. So mass times acceleration, Sarah's onto something here, equals the magnetic force. I know that this is equal to QV times B. Okay, and I know A is V squared over R. When do I make that change? When do I make that change? Put it in the chat. Why am I allowed to say that? Okay. Oh, wow. I feel like such a lucky duck this morning. Attune, there is acceleration. There's a force and there's an acceleration. There's an acceleration, and I'm saying that acceleration is equal to V squared over R. But you're on to something, Attune. I think you want to say that, but in a different way. There is acceleration. but there's something that's because we are in UCM. Yes, anytime I'm in uniform circular motion, I can set my A equal to v squared over r. What is uniform circular motion? It means I'm in a circular path and my speed is uniform. So my speed is constant, right? Speed being constant does not mean there's zero acceleration, right? Just looking at this trajectory, even though I don't change my speed, how can I say, why am I still going to say there's acceleration even though there's no change in speed? How do I know there's acceleration here? Put that in the chat. Type it up as fast as you can, right? We got a lot to cover today. Change in direction, right? So acceleration attuned is change in velocity, and velocity has two parts, speed or direction. So here are the cases where I have a non-zero acceleration. If I change my speed only, if I change my direction only, or if I change both, right? All three of those cases are cases where I have some acceleration, okay? Yeah, but I believe what you meant to say was if there's constant speed, right? Yeah, so if I'm traveling in a circular path at constant speed, I'm allowed to make that change, right? A equals v squared over r. Now the cool work can be done, all right? Because I can get rid of one of these v's, right? So I have m v over r equals q times v. And if I solve for m, it becomes q v r over the speed, right? Which tells you some really cool things. Okay, so first of all, let's go over the first part of the problem, right? If my field points into the page, okay, and I'm going to need another color marker for this. Ugh. Okay, if the field points into the page, all right, which in our lab would probably correspond with down, right? It's pretty easy to create a magnetic field that just points straight down into the floor. So the page is the floor, right? This is a bird's eye view, right, Eric, Bev? And there's two paths it can take, right? One, it can take a circular path this way, and the other can take a circular path this way, right? What determines which circular path it'll take? It's the charge, right? So if it's positive, which direction will it go in? And if it's negative, which direction will it go in, right? All I gotta do is use my right-hand rule. Where would a positive charge go? If my velocity is pointing this way, cool. My middle finger is the field, boom, points in it, and it experiences the force up. So the positive particles go here, okay? Not only that, my left hand, my negative particles, look at the force pointing down, go there, right? So, so as you can see, excuse me, is that if this is my detection screen, right, and then this is my detection screen, that positive particles will collide with this detection screen, and negative particles will collide with that detection screen. What's a detection screen? It's any kind of screen or surface that can register a collision with a really small object. This is exactly how cameras work, right? You have digital sensors, and anytime a light particle hits the sensor says, woohoo, there it was, right? Yeah, so in the lab, what these really are just like really expensive camera sensors, okay? And okay, so the protons go there and the electrons go there, and the second thing you got to know is, well, which path does the proton take? Which belongs to the electron? Wait a second. Did I give it? No, I didn't give it a second part of the problem. Okay, so already here, you can see all objects are in the identical magnetic field. They have the same magnitude of charge, right? It's the elementary charge, 1.5 times, 1.6 times 10 to the negative 19 coulombs. They all are launched with the same speed. So the only thing that affects the radius, right? Alternatively, you can write this. The only thing that affects the radius is the mass. And a more massive object has a greater radius. If you think about this, you should be able to explain this without math in a paragraph. Why does a more massive object have a larger radius? I want everyone to think about this for a solid minute. I'm actually looking at the clock. It's 10:17, 15 seconds. I'm not going to come back here until 10:18, 15 seconds. All right? Think about it. You can use this formula to help you, but you're not allowed to reference it mathematically. Why should I expect the more massive object to travel in a bigger circle, right? We'll have a larger radius, okay? Okay, so I've given us a little bit more than a minute, and I think that's okay because this is worth thinking over. And I'm going to go over why I think it's true, okay? If my force is equal to, well, if the magnitude of my force is equal to the magnitude of my charge and the velocity in the magnetic field, right? It's clear that every particle will experience the same force, the magnitude, right? Whether the force is this way or this way. I don't really care, but the magnitudes of these two forces are going to be the same, right? That force, right, is equal to my mass times my acceleration, all right? So if you really think about it, the object with a larger mass experiences a smaller acceleration, right? The object with a larger mass experiences the same acceleration because Q, V, and B are equal, right? That's like the big part of your argument. Like, if the smaller massed object was launched faster, then I'd actually have no way to predict which one has a bigger radius circle, right? So I'm not even going to look at V squared over R here. All I'm going to do is, well, if the more massive object accelerates less, then it'll turn less, right? That's like thinking of if I throw a ping pong ball, if I drop a ping pong ball and I drop a bowling ball and there's like a horizontal wind, right, going on both, the bowling ball will turn less, right? It'll be affected by that horizontal force less, and it'll turn less because it's more massive, right? Because it has a smaller acceleration. That's the way I want to think about this problem, okay? I don't even want to solve for the actual numbers because they're kind of ridiculous. Yeah, I kind of messed up when I created this problem. So if you didn't get it, it's fine. Okay. I don't really think there's a need to go over it, right? Because it's just plugging in these numbers. Right? You just plug in the mass of an electron, the velocity that I gave you. Why doesn't this make sense? Because the velocity exceeds the speed of light, which is 3 times 10 to the 8 meters per second. So why did I do this? I had like a certain radius in mind that I wanted to solve for. So I plugged in the value for the mass, and then like a value of magnetic field that's reasonable, and then I solved for with a radius in mind, right? So then I plugged in the mass, and then like a magnetic field that's reasonable to construct in a lab, and then I solved for the velocity, and I got 2 times 10 to the 14 meters per second. So what that instead tells me is that I should have chose a much smaller velocity, and then also made my magnetic field a lot smaller too. Whoops. Okay, yeah. You got some really bad numbers because I just didn't do it right. What's up? Who cares? I don't care about the numbers. If that's what I care about. If you got here, you're fine. That's the physics, right? Now, whether you can plug and check in your calculator, why should I care about that? Why should anybody care about that unless you're an engineer and the calculations like mean like whether or not the building's going to collapse? But otherwise, why would I care? Huh? Okay. So let's move on to the next topic. Okay. And this is romance. Okay. I know. Get really pumped. Yesterday, love was such an easy Okay, so here we go. Today we're going to be talking about wire romance. Super hot, okay? Ooh, ooh. What do I mean about wire romance? I'm talking about the force between two current-carrying wires, right? Here is a basic postulation that I will give you, okay? Nice. That's the height I want. Okay. Here's a basic premise I'm going to give you, all right? If I have a wire here, and it carries current this way, and I have a wire close to it, and it also has a current going this way, right? How this is achieved, I don't know. Maybe these are both part of a parallel circuit. Maybe they're both part of their own circuits, you know, like maybe this has a battery here, and this has a battery here, and this current goes counterclockwise, and this current goes I don't know, right? But I don't care how it happens. All I care about Chris, that is the greatest force on earth. Oh, you guys just made my day. I was so tired. I think I slept at 5 and I woke up at 8:30. I'm so tired, but that really just made my day. Thank you. Where were we? Oh, yes. So I have two wires and they're carrying current side by side. And I'm going to say these wires feel a force. This wire experiences a force from that wire. This wire experiences a force from this wire, and this wire experiences a force from this wire. I'm not going to tell you what the force is. Like, they're either going to attract, okay, or they're going to repel. Ew, gross, not my type. Okay. We're going to go over which case this really is, okay? Right? So what's going to happen? Either one of these cases is going to happen, okay? We're not totally concerned right now about which one it is. I'm more concerned about why. Why should I expect there to be a force on these two wires? And if you need a reminder about this, remind yourselves, where does magnetic force come from? And what does the magnetic field, where does the magnetic field come from? And what does the magnetic field affect? This is straight from yesterday. Hold this in, type it in the chat, but don't enter it. All right, I want us to enter this all at once, okay? So I'm gonna give us a minute to type this up. Why should two current-carrying wires exert a force on each other? And remind yourselves, where does the magnetic field come from? What does the magnetic field affect, okay? All right, so I got my new pot, right? It's this is actually my first teapot, and I don't use it that much. I only use it for a very special Korean green tea, from the mountains. Most of my green tea is Japanese. Let's type it in the chat. Why should I expect there to be a force between two wires? Press enter. Okay. I'm looking for a lot of responses. Sarah's first, right? Itamar. All right. Right? Yeah, so moving charges, if they generate magnetic field, that means this wire generates magnetic field all around it. If this is a moving charge, if this has moving charges in it and it experiences a field here, then it'll experience a force from that wire. Likewise, this wire has its own field, right? And it'll affect this wire too, because this wire is moving itself, right? Let's take a look at now which case it is. Will they come together, or will they no? Okay, so let's kind of see what's going to happen. Let's look at the left-hand wire first. All right, so this is the left wire. Let's use our right-hand rules, okay? Where is the field pointing on this side? Where is the field pointing on this side? It's either in or out of the page. And I just got to use my right-hand rule to see how the field is going to curve. Is it going to curve around this way, or is it going to curve around this way? All right, which way is it going to go? It is going to go this way, right? Which means from this side it comes out of the page. Right, and on this side it goes into the page. This was from the very first worksheet from last week. All right, I mean from our unit from last week. All right, I see most of us have turned that in. In order to better reinforce that, we're looking at this one more time. All right, so now let's look at if a charge is traveling up. Let's use our other right-hand rule, the A rule, all right? So actually they're both A, right? Because like one is like A and the other one is like A. So the one is, I think, just more like a general, like things are good. And then the second one, I think, is like you are good, A, all right? So let's use the you are good rule, okay? To see where the force on this charge is going to point. Right? My pointer finger has to point in this direction. My middle finger has to point in, right? And oh my gosh, there's a force. Where's this force pointing? It's pointing to the left. Oh my goodness, this is like an extension of our homework. Fantastic, all right? Now let's look at the, so this was looking at the magnetic field of the left wire, and the force on, we're looking at the force on the left on the right wire, right? That's what this is really about. Now let's look at the other scenario, right? This is the right wire, the right-hand wire. Again, if I use my A, everything's good. Everything's good. Self-isolation's gonna end in like 2 months. Everything is so good. It's gonna be the same way, okay? It'll be the same way with a roof right over our heads. Is this love, is this love, is this love, is this love that I'm feeling? Oh, all right, so cool. So this is a right-hand wire, the field due to the right-hand wire, but what we're really interested in is the force the right-hand wire exerts on the left-hand wire, right? So to do so, yeah, these are positive charges, we're assuming, right? That's why I'm using my right hand only. If they were negative charges, I'd be using my left hand, right? Is this left? Is this left? No, it is right. Okay, so let me look at this positive charges going this way, right? And guess what? Let me do the rule, right? Velocity's up, force is out of the page, so A, right? And my field points out of the page, and oh my goodness, the force points in the other direction. I knew that though. As soon as I saw this, I knew that this one. So as soon as I saw that this wire was experiencing a force this way, I had to know that this wire experienced the force this way without even doing the second example. Why is that? What very simple rule that we learned very early on tells me once I know the right wire experiences a force to the left, I know the other wire must experience an equal force to the right. Which rule or principle says this? Chris has named it without naming it. Newton's third law. Exactly, right? So Newton's third law tells us so many things, right? I do believe Newton's third law we use to prove conservation of momentum. Okay, right? Why? If you guys are curious, let's do a really quick review about that. Why does Newton's third law say conservation of momentum? This is change in total P is 0. Because anytime I have a collision between two objects, this is 1 and 2, the force 1 exerts on 2 is equal to the force 2 exerts on 1. So the impulse that 1 feels is force 2 on 1 times the time. The impulse that the second object feels is the force 1 on 2 times the time. And guess what? The times are equal because both objects perceive a collision for the same. It wouldn't make sense if the times were different, right? Like, if you guys have been naughty students and I hit you in the face, right? Like, my hand would say it was in contact with your face for like X amount of milliseconds, and your face would also probably say it would perceive the same time, right? And it was in contact with Mr. So's hand for like, whatever, how many milliseconds too. So because the times are the same, and Newton's third law says the magnitudes of the forces are the same, the impulses are equal, but you got to remember the forces are in opposite directions, so one is negative, which means the total impulse is 0, which means the change in total momentum is 0, okay? But we also must remember nothing is ever in contact. Yes, Itamar. Okay, wait, but for this to be true, yes, okay, so also, why are we assuming that the charge generally is on the inner side of it? Huh? I don't understand your question. Can you reword that? Or can another student try and rephrase it if they know what Ayanava is asking? For the left wire, why are we looking at the right side? Because there's an object in its right side. Is there anything here? No. So if I'm looking at this wire, I just want to look at what's happening in this region. So, yeah. For this right wire, is anything happening here? No. There's an object here, so I want to look at that one. Okay? There is a field on the outside. Oh, but for general cases, we look at everything. But for instance, like we will only look at regions where there are moving charges in those regions. So in this example, because there was no moving charge here or no moving charge here, I don't really care about what happens here. I don't really care about what happens there. His other question, Ainava's other question was about, well, why don't we see this in real life? The currents usually are too small. The wires are too far apart. Small current means small field, right? It also means slower charges. So F is QVB. You're decreasing V and decreasing B. But the other really cool thing is this thing called a coaxial cable. When I have a wire that's just one thing and it plugs in here, what that wire really is a cylinder of copper and a hollow cylinder. And then inside is a thin wire of copper. We call them coaxial because they share an axis. So that wire basically looks like a tube of aluminum foil here. And if I had like another wire inside. And how this works is current goes in here, right? And here, I can show you. Here's how that circuit works, okay? It looks like this. So if this is your device, if it's somewhere here, right? Let's say I have an electronic whatever. Let's say this is my phone. This is exactly how my phone charges, okay? Even though it looks like one cable, when I plug it in, it's actually two, and it looks like this, okay? So maybe the current goes through my pencil wire here into my phone, and then the current goes out of my phone, and it goes out through this sleeve part of the wire, right? No one says wires have to like go side by side, right? No one says a circuit has to go like this and then this. Like the way the wires are shaped doesn't really matter. So I could go like this and then I can come out like back in, right? Why is that important? Because if I have one current going this way and then the other current going this way, the field generated by this wire goes this way, but the field generated by this wire goes the other way, and they cancel. So these two wires generate no external magnetic field. Now inside there is some magnetic field. It's really weak though, right? But the really important thing is whenever I have a coaxial cable, it produces almost zero external magnetic field because the two currents are going in opposite directions. So they'll cancel, okay? Oh, I just realized I've been streaming this whole time. My laptop isn't even charged it's not even charging. It's almost dead. Okay. Ooh, that was a lot. When do I get this case? It would be non-romantic. What do I mean by that? If my wires look like that, right? Now let's look at this case. Right-hand rule. A charge going this way. Where's the force it experiences? This way, this way. Oh, wow, that force is out. Then by Newton's third law, I know this force is out. Yeah, so this is one of those few cases where opposites don't attract, right? And like things attract. So this means, yeah, it means if you're vibing, right? And then your partner's also vibing in the same way, and you will attract. And if you're vibing one way and your prospective partner's vibing the other way, and you guys are going to repel. All right? F. Now, the homework I'm going to post today is only one problem. Here is a short preview of it. It's very exciting. Okay? That's it. It is a multi-part problem, though. All right? But don't freak out about it. Mr. So if you have two moving charges moving side by side, oh, who can answer Chris's question? Right? If I have a positive charge here and a positive charge here, and they're both moving with this velocity, I know that they experience a magnetic attraction. That's what we did in the very first one when we had parallel wires. But we also know that they experience a electric repulsion. I also know that in addition to all that jazz, there is a third force at work. What is it, everybody? What's the third force acting on those two objects? Gravity. Do you know some teachers have their students draw free body diagrams like this? Absurd. Anyways, so how do I know if they attract or repel? Brosophinas? Just calculate all three of those, right? And see which one's bigger, FB plus FG or FE, right? So we already know that gravity is so weak, it's probably like inconsequential between these two. So the real question is, how fast is this going, right? The faster it is, the greater the magnetic force, right? So the faster they go, the more they'll veer towards each other. The slower they are, the more they'll veer away. Isn't that cool? Okay. Last thing I want to talk about is the force on a wire. There is an additional formula for the. Let's say I have a magnetic field. It's uniform, which means at every one of these points, the magnetic field points in the same direction. I've already drawn that, right? So it's uniform in direction. It all points into the page. Why do you always pick into the page? Because it's much easier than drawing a dot with a circle, because my circles are really bad, as you can see. Your axes aren't too hot either, -1. Yeah, let's say I have a wire here. When I say it's uniform, it means it's also uniform in magnitude. So maybe this is like 3 Tesla, 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 blah, 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 right? Where Tesla is the unit for magnetic field. Okay. Chris asked one more question. I don't have time for that, Chris. We got to go over this problem. So if I have a wire and it has a length L, and it has some current going through it, I don't know what it is. I want to know the force on the wire. Well, I know if I zoom in here, right, and I look at this one charge, right, the force on that charge is QVB. So if I want to find the force on the wire, I basically just have to find how many charges are in there, right? I just got to multiply this, right? So force times the number of charges moving equals the force on the wire. How do we do that in terms of only what we are given? Wait, sorry, can you write that a bit larger? Basically, I want to find the force on the wire, but only in terms of I and L, okay? Yeah, so I think a nice way to do this is to work backwards. And it's a really nice exercise in trying to derive the formula. Like you can kind of, it'll make more sense if you make the connection yourself, right? So I'm going to tell you right now, the formula for the magnetic force on a wire in a uniform magnetic field is IL times V. One way to think of this is to say I is Q over delta T. And L over delta T is V, right? There are other ways of thinking about this too. And I'll leave it up to you. But this is a pretty important formula for the problem I'm going to give you. It's a pretty neat application of magnets, okay? And that's what I'll leave you with, all right? We will go over this problem tomorrow. I know this is, do you guys find this a little bit too fast-paced? The problem is that we basically only have the rest of this week to cover magnets with the way the pacing's kind of laid out, and maybe a little bit of next week. So that's why it feels a little fast. Does this feel a little fast that you have another worksheet due tomorrow? Even though it's just one problem, it is just one problem. And if I'm comparing it to school, it's still less than like giving you a worksheet with like 5 problems on it every day. But if it feels like a lot, just let me know. I'm going to post it anyway. All right, we'll go from there. It's due tomorrow morning. If you feel like it's too much, I won't assign something tomorrow, right? But today's assignment still stands. Okay? Thanks, Sarah. Yeah, so be on the lookout for that. I'll post that right after my Regents class today. My Regents class is going to be a little long because the stream got copyright flagged yesterday for no reason. Yeah. All right. So I got to cover a little bit more with them today. I'm still confused about how we go from QVB to. It's not QVB to QLB. It's QVB to ILB. So if you want to, in your notes, to make this formula make a little bit more sense, it's simply, this is a force on a moving charge equals the velocity of the charge times the charge of the charge times the magnetic field strength that the charge is in. It's very similar to electric force equals QE. Right? This is a formula for the magnetic force on a wire, because a wire has moving charges in it too, right? So the magnetic force on a current carrying wire equals the length of the wire, the current traveling inside the wire that I measure with an ammeter or whatever, okay, and the magnetic field that the wire is in, right, which is this, okay. The simplest connection between these two formulas is I know that I is Q over T, and then this becomes Q times L over T times V, and L over T is V, right? It's the velocity. That's the speed. There are other ways of looking at that, all right? But if you're not convinced, there's some resources online. But I really got to go, all right? Bye.